Let's talk about these two sets of dogs. We see the top picture of dogs has 4 dogs. One dog weighs 70 pounds, the next dog weighs 73 pounds, 58 pounds, 60 pounds. And if we find the mean weight of this group of dogs, the mean is 65.25 pounds. The bottom set of dogs is much more spread out. But the mean weight of the bottom set of dogs is pretty close to the mean weight of the set of dogs on top, 64 pounds, just 1.25 pounds off. However, these two sets of dogs are really different. The top group of dogs are all about the same size. They're all medium-ish dogs. From the biggest to the smallest, the range is only 15 pounds. Whereas the bottom set of dogs, the range is 95 pounds. From the biggest dog of 125 to the smallest dog, 30, that's a lot of difference. When we talk about measures of variation, we're talking about how spread out the data is. Range is one measure of variation that describes it very straightforwardly. But what if all the dogs were, what if you had 100 dogs that were all about this size, except in walked the big one and the small one from the other group? All of a sudden, the range would be totally changed by that big dog and that small dog, even though there were 100 medium-sized dogs. The range doesn't tell us much information other than the biggest to the smallest. We don't know if most of the data is close to the middle or if all of it is really spread out. That's the value of the standard deviation. Let's see, I think I've got this for us here. There we go. Our text has a nice layman's definition of standard deviation. Essentially, it's the average distance that each data value is from the mean. So on average, are most dogs pretty close to the mean, or on average, are they really far away? Let's see, there we go. Down here we see the standard deviation is 30.7. That means that on average each dog is like 30 pounds away from the mean weight. Whereas this top one, the standard deviation is 7.4. On average they're about 7 pounds away from the mean. They're clustered much closer to the middle. Let's look at another example. We've got 3 data sets. We don't see the data. All we know is the standard deviation. The first one has a standard deviation of 2.7 inches. The second has a standard deviation of 5.5 inches. And the third has a standard deviation of 10.3 inches. We can't see the data. We just know the standard deviation. Which data is the most spread out? So take a sec. I'm going to pause and make your guess. Did you make it? Okay. The data that is the most spread out is the data with the biggest standard deviation. So data set 3 has data that is the most spread out. Data set 1 has data that's the closest together. The bigger your standard deviation, the more spread out your data is. So if you're trying to predict something, if you have a small standard deviation of data from the past, let's say we're talking about lifespan of a certain species. So we've got a whole bunch of data of lifespan of that particular species. If the standard deviation is really small, then that means that they all end up being really close to the mean. So if you're going to predict Well, if they're all generally pretty close to that mean, then you could probably predict pretty reliably. But if the standard deviation is huge, then that means no matter what the average lifespan is for that species, the standard deviation is huge. That means that in the past, at least, it's been all over the map. It's been a lot smaller than the mean, a lot bigger than the mean, but when it all balances out, here's our mean lifespan. It's much less reliable to predict.